This work wouldn't have been possible without my collaborators, Connor, Zhuoer, and Tiffany from ASU, as well as Tudor Dumitraș from UMD. Adding another data point about vulnerability lifecycle to what Nicolaos was just showing, we could plot the number of papers about vulnerability detection in the last decade, and we see that there's an increased interest in the research in the topic. Moreover, we also see that the number of vulnerabilities disclosed is also increasing over time. This goes to show that we're getting better at finding vulnerabilities. However, time and again we're reminded of the potential significant impact that exploits might have against those vulnerabilities. And this shows us that exploits still remain one of the principal tools for cybercrime. So one natural question is, are our techniques for identifying exploitable vulnerability also improving? How are we able to identify exploitable vulnerabilities? First, we could do manual or automatic exploit generation or detect exploits in the wild, providing hard evidence, conclusive evidence about the existence of exploits. We could use this evidence to track exploits in platforms such as the CVSS temporal or commercial platforms as well, and reactively capture this fact about the existence of exploits. However, those approaches do not provide any evidence about the non-exploitability of exploits, and for that, we have exploitability assessment metrics, which intend to capture the likelihood of exploits, and they're generally performed through heuristics. Some example metrics are the CVSS exploitability, Microsoft Exploitability Index, and Red Hat as well. How are those exploitability assessment metrics performing? We could design a simple predictor, predicting true everything that's above a threshold, and measuring the precision, which is the fraction of predictions that are actually known to have functional exploits. We could plot the precision for different score values and across metrics, and we observe that precision is not great for all the metrics that we considered. This is because existing metrics tend to yield many false positives in actually predicting which vulnerabilities are being exploited. Now, our research agenda is trying to improve the exploitability assessments, in particular to data-driven techniques. And our goal in this paper is to develop a system to estimate exploitability from data. Estimating exploitability from data, it means actually approximating the expected value of exploitability over time. We call this concept expected exploitability, and we use it to build a platform to help practitioners improve their assessments. To understand the challenges of building such a system, we look at the 2018 Internet Explorer vulnerability, which allowed remote code execution. And if we use features available at the time of disclosure, those that are used by existing metrics, we could predict that the exploitability is quite difficult. However, what we see is after disclosure, technical artifacts and write-ups are published, and in this case, researchers determined that those write-ups enabled exploit development, and it was actually the cause of exploit development. So what we see is that all the information available post-disclosure might provide opportunities for us to improve our predictions. However, we need to capture this information in our exploitability assessments. We provide a time-varying view of exploitability in the paper, which is influenced by the publication of those artifacts. And using this view, we develop a machine learning system to compute and track exploitability over time. The second challenge can be highlighted through a 2019 Cisco router vulnerability, in which we could use write-ups for assessments and use features from prior work on data-driven exploit prediction. However, what we see here is that a proof of concept is published later after disclosure, and we might overlook this proof of concept based on prior work observations that the existence of proof of concept exploits is not a good predictor for functional exploits or attacks in the wild. But what researchers discovered is that the code of this POC was found in exploits in the wild. So if we do not take into consideration features from the content of the POC, we might overlook useful features for predicting exploitability. The challenge being that we need to think and design and extract features from those POCs, looking at both the code and the descriptions in natural language. The second contribution is we design a set of PoC features which we determine to be semantically linked to the difficulty of creating functional exploits and show that those features complement those from prior work. The third issue that we have is highlighted by looking at Eternal Blue, the vulnerability behind the NotPetya and WannaCry, for which it was determined that the exploit existed for 5 years before public disclosure. So if we look at Eternal Blue in our ground truth, we might be dealing with an incorrect label. Now, such biases in ground truth for exploits have been acknowledged before since 2010, but not investigated before. And those biases cause label noise. In the machine learning literature, this has been investigated numerous times. However, from other domains, we see that label noise mitigation requires domain knowledge. The challenge here is that we need to address it by first understanding the characteristics and potential impact of noise. The contribution being that we characterize and quantify label noise as it relates to exploit prediction, providing a mitigation strategy for it. Let's look into all those contributions to more detail, starting from the time-varying exploitability, which we compute on vulnerability data set for over 20 years, collected over the last 20 years, and over 300,000 artifacts that we collected from public sources, as well as exploit evidence from multiple sources. We want to see what are the factors that enable exploit development, and we measure how soon exploits become available once artifacts are published. The dotted line here shows instances in which exploits become available soon after artifacts publication, highlighting that exploit publication is highly correlated with artifact publication. We use this to hypothesize that exploitability changes over time, and those changes are reflected in publication of artifacts. Now, we use this intuition to develop an expected exploitability system to predict the likelihood of exploits. It uses supervised machine learning, and in deployment, it continuously estimates exploitability. We measure the performance against static metrics, as well as a data-driven approach for predicting attacks in the wild. This EPSS system was based on handcrafted features, and we measure the precision and the recall of our classifier. Looking at the performance, static metrics do not perform well as expected because they do not capture post-disclosure information. Interestingly, other data-driven techniques for exploit prediction in the wild can improve a little bit, showing that features might be useful for our domain. However, our system has a substantial performance boost over these baselines, showing that if we think about tailored data-driven solutions, we could make meaningful improvements in exploitability assessments. Now, what are some of the things that enabled this performance boost? First thing is the novel features that we develop. Going back to the factors reflecting exploitability, we see that prior work features are quite correlated with exploits, so they're likely to be good in predictions. However, we observe that proof of concepts are some of the most correlated artifacts with exploit development. And digging deeper into this, we observe that proof of concepts are designed to trigger the vulnerability, and they cannot always be easily weaponized. And perhaps this is one reason why their existence is not very well correlated with the prediction of exploits. However, what we observe in our paper is that any functional exploit needs to trigger the vulnerability, which is a common thing between the POC and the functional exploit. And showing that proof of concept exploits and functional exploits share characteristics in terms of code complexity. POC code complexity reflects exploit complexity, whereas the descriptions in the POCs might tell us what steps are required for exploitation. We build a feature extraction system that uses program analysis and NLP to extract two types of features. And we show in the paper that those features that we extract can complement these from prior work. All right, so the next thing that allowed us our performance improvement is this investigation of the label noise robustness. And in particular, looking at biases in ground truth, we see that those are inherent to the problem because exploits might be kept private or published only later. So the probability of an exploit, even though we don't know about it, is greater than 0. This has been acknowledged for 12 years, but not investigated before. And in the machine learning literature, we know that it results in class-dependent noise, which could impact performance. However, we observe that individual sources of exploits might also have biases. For example, Symantec did not have a product for Linux, so a Linux exploit might not be available in a Symantec ground truth. This is indicative of feature-dependent label noise. And this category of noise is considered an open problem in the ML community. Now we want to test the evidence for feature-dependent noise, and we perform statistical tests for independence between sources of exploits and features of the vulnerability, showing that we could rule out independence for each label source with at least 4 features, indicated that all label sources might depend on some features, and then our problem of exploit prediction is subject to both class and feature-dependent noise. We measure the impact of this noise in the paper by simulating noise injected in a training set and concluding that it could significantly degrade the performance of the classifier and that we need a mitigation strategy. We designed this mitigation strategy by embedding it into the training phase and observing that off-the-shelf solutions do not fully address the problem constraints. And our loss function, called FFC, uses prior about noise distributions and probabilities of noise. The key idea behind it is that it reduces the penalty for mistakes on instances that might have noisy labels. We show in the paper that it can successfully correct performance drops caused by both types of, both class and feature-dependent label noise. To wrap things up, exploitability evolves over time, but we could capture this evolution and predict the likelihood of exploits. We do this through a system called Expected Exploitability. And also, while prior work features might not be sufficient for exploitability prediction, we could think about the content of the POCs that could complement those features. And finally, while exploit predictors are affected by ground truth biases, if we characterize and measure the impact of those biases, we could provide a mitigation strategy against it. Before I take questions, I want to note that we implemented this into an online platform, which provides tools and an API for practitioners to improve their security and exploitability assessments. So, thank you.